Hello.
On it. Okay. I heartily welcome one and all to the AWaRe 2025, the first international conference on advances in water resources. In the continuation of inaugural ceremony, we now forward to keynote section. It is my great honor to now introduce our first keynote speaker, a visionary in computational hydraulics and groundwater modeling over more than 30 years, Professor T.I. Eldo, professor in the Department of Civil Engineering, IIT Bombay. He completed his BTech at Mahatma Gandhi University and went on to earn his MTech and PhD from IIT Bombay. And he has published over 200 journal articles, hold a granted patent, has 2 more pending, and has authored numerous book chapters. He has earned prestigious awards and fellowships, including the German Research Fellowship, Taiwan National Science Council Fellowship, DAAD Research Fellowship, Dual Jal Vigyan Puraskar Award, and the title of Eminent Water Resource Scientist. He is a fellow of the Institute of Engineers India, Indian Society of Hydraulics, Indian Water Resource Association, and a member of the National Academy of Science, India. Please join me in extending a warm welcome to Professor T.I. Eldo, sir, and I would like to request sir to deliver his section. Please.
Huh? 25, I can finish by 50. Huh? Okay, no problem. Okay, so thank you very much for the introduction. So I'm very happy to be here in NIT Bhopal. Actually, every year I used to come. So this year, anyway, in this occasion, which is this Advanced and Water Resource conference, which is mainly organized by Dr. Harshit, Dr. Duja, and then many of my say students and friends. So I'm very happy to be here. I am very happy to address all of you. And since we are having a long inaugural session, so now so we are having less number of participants also, no problem. So since both are going in parallel. So without wasting much time, though I work in most of the areas of hydraulics. So as Dr. Harshid informed me, since in groundwater nobody is there to give a lecture, so please give a lecture on groundwater. So that is why I have chosen this particular topic. So groundwater management. So for using simulation optimization. So as all of you know that groundwater is one of the most important aspect of our life. So actually you see that as per an estimate, almost 99%. You have got a pointer? Pointer is there. You have got a pointer. Yeah. So you see that though we have so much water, so almost 99% of the available fresh water is from groundwater only. So that way, groundwater is so important, especially many countries, including India, almost 70 to 80% of the water supply is coming from groundwater. So that way, groundwater having say so much of importance in our water resource. So when you talk about advanced water resource, so surface water, groundwater and surface water interaction, all those things are very, very important. So that way, you see that when you talk about groundwater, two important aspects is there. One is the quantity of available fresh groundwater. And then second aspect is the groundwater pollution or groundwater contamination. So before 1970s or 1980s, so most of us thought that since the groundwater we are pumping from say underground, I mean from the aquifer system, so the water will be very pure, and that concept through that concept only. So everybody was dealing with the groundwater, but then various studies in 1970s, 80s, 90s, all those showed that the groundwater is also highly contaminated, and it is a big problem. So groundwater contamination is a big issue, not only in India, but throughout the world. And then due to this awareness, many of the advanced countries like European countries and America, they started even say very strict laws to stop this kind of contamination. And then wherever contaminated, they started the remediation kind of activities. So actually in India, unfortunately, though India is one of the most, the country where maximum groundwater is taken from the for the various uses like the drinking, then agriculture, all other activities, but still there is no such plan to stop, since actually you see that as all of you know that surface water and groundwater is very much interconnected. So when we are keeping say a contaminant on the surface, so that will be leaching down. That is the typical example is our landfills. So wherever landfills are there, that will be definitely going back to the aquifer systems. So major contaminants, what is of course industrial contamination is there, and then also natural contamination like arsenic contamination due to overuse of the usage, and then also seawater intrusion. So these are all the major contamination problems. So as I already mentioned, India is the largest user of groundwater in the world, and actually much more than even China and America. And also, say for example, India, as I mentioned, 60 to 70% of the drinking water supply is coming from the groundwater, and even many so the states, the irrigation needs are also met through the groundwater. So now, say as you know that by 2050, the available water resource for per person, since due to our increase in population, the availability of water itself is very limited. And then you see that we need to say this shows how it will be behaving. So only 35% of Indian wells, so say whatever the way, whenever the groundwater is concerned, you see that it is just like a bank. Whenever we are depositing, we can take back. But if you keep on taking, then of course there will not be any money left in the bank, so on your own account. So similarly, groundwater is also, since many places like Punjab, Haryana, Delhi, etc., all these regions, since they keep on pumping from so deep wells. So in all these areas, there is a scarcity of water, and then it will be a big problem later. So this shows another issue. This first map shows groundwater status in India. You see that many of the states, like this red zone shows the wherever the high stress will be there of the groundwater, and then many other zones like yellow also critical. So that kind of things are there. And then quality issues concerned, India is highly same. Most of the parts we have got high contamination. So you see that say different kinds of breaches. So as per Central Groundwater Board, the breaches occurred in many locations are shown. So and since most of our rivers are highly contaminated, due to this reason also we'll be having the groundwater contamination will be taking place. So that way you see that groundwater is concerned, you see that it is on a local scale as well as a country scale, it is a big problem. So problems with the groundwater, as I mentioned, one is the quantity of groundwater. So due to many locations, we are having overdraft or mining or subsidence, all those things, issues. Then coastal region, coastal aquifer, seawater intrusion is a big problem. And then say but the other issues, as I mentioned, groundwater pollution, you see that the most of the country, many areas are highly contaminated due to natural contamination, agriculture contamination, then industrial contamination. So like that, the contamination, the most part of the areas are highly contaminated. So this is a major issue. So compared to surface water, the groundwater, the main issue is that in surface water we can see what is happening, and we can easily take the samples and then measure, and then we can easily visualize what is the way it is happening. But groundwater is concerned, it is, as you all of you know, that it is not so easy. Whenever we are having a well, that local region, if any contamination is that we can identify, or all these details, that way we can take it. But say whatever is happening in a say spatial variation or temporal variation, it is very difficult. So there modeling is very important. So those surface water in rivers or lakes, without modeling, with a very easy way we can collect the samples and then we can visualize. But groundwater, say, though we can take samples from the open wells, bore wells, etc., but without modeling, it is very difficult. So as all of you know, that the models are representation of real systems. So we are trying to say simulate what is the in reality as far as what is available, the maximum possible way, by putting number of assumptions. So understanding groundwater system, we need, and then we need to go for prediction. What is how the, whether with respect to quantity of water, how much water is available, and then also we need to go for monitoring the network, and then so groundwater models. So that way we can have physical model. So physically you see that we construct samples. I mean, say to scale we can construct the models, but that is very large scale. It is not so possible. And so that way, now due to the last 3 decades, we have got so much of changes taken place. Of we have got computer modeling, as computer simulation has become so common. So that way, computer modeling is only, simulation is the best way the groundwater, say, to do the assessment, to do what is happening with respect to spatial wise as well as temporal wise. So in the modeling is concerned, we have to collect data, then we can go with respect to the temporal variations we can take. So I think something is, yeah. Okay, so that way we need to see. So that way numerical modeling, so what we are doing, we are converting the governing, so we can have a, so luckily we are having sufficient mathematical concepts are available as far as groundwater is concerned. We have got a set of partial differential equations, and then we can, based upon that, we can construct number of modeling. And the last 3 decades, we have got very efficient models using various numerical techniques like finite difference method, finite tunnel method, boundary element method, finite volume method. So like that, whichever region you want, or even for the big country like India also, we can make appropriate modeling as far as the groundwater is concerned. So the latest trend, since though this is a keynote, I would like to show some of the results which my students are working for the last few years. And the latest technique compared to this numerical simulation is so-called meshless method. So I'll be mainly focusing on meshless method, how we can use this kinds of technique. So as far as modeling is concerned, there are so much of packages are available. It is the last 4 decades, so many models are developed. So typically based upon the finite difference methods, like which is the most commonly used model is called mod flow, and MT3DMS, say for contaminant transport. Then we have got RT3D, then so finite element based model, FE flow, seawater intuition models, then COMSOL models, Sutra models. So many models are available. So here in all these models, all the available typical industrial based models, so there these are all either finite difference or finite element based models. And in all these models, our issue is that we need to see that so here say we can have the models based upon so here, okay, so I will just use a so as you can see, we are having the based upon finite difference finite element model. So there we need a particular mesh, and then meshing or remeshing So if you are developing a model and if you want to modify that, it is a big problem. And that is why this meshless method came into picture. And it is now, so you can see the difference between various kinds of modeling tools like finite difference method, finite tunnel methods, then meshless method. So in finite difference method, we are putting number of grids like this, you can see. And then, so in finite element methods, what we are doing is, so we are having elements like this. And then meshless method is concerned, we are having only put a number of nodes in the domain as well as the boundaries. And then based upon that, since, as I mentioned, my main emphasis here is what are developments in this area. So that is why these latest techniques I am just introducing here. So we are throwing some number of nodes throughout the domain and boundaries. And this, say, based upon that, these nodes we discretize, or we use the partial differential equation to represent the domain, and then we try to solve the problem. So advantage is that if you want to modify a model, already developed a model for a particular area, you can keep on changing without much difficulties, and then we can introduce many aspects at any time. So that is the advantage of this meshless method. So here you see that an aquifer with almost 250 square kilometer, it is modeled using even simply using around 250 nodes, only nodes. There is no connectivity, simply throwing nodes throughout the boundaries and domain. And that nodes, you can see that we can truly represent. And then it was already well proven that yes, this is good enough even to, without any mesh or without any grids, we can represent the system, and that will be giving good results. So that is shown in this figure. You can see in this right hand side figure, you can see how the modeling is done for a large area like a 250 square kilometer area. You see that as I mentioned, this without in groundwater sustainable modeling, without modeling we cannot survive. So already 1940s and 50s, the finite difference based models, 60s, it has started using like ModFlow and MT3DMS in 70s, 80s. Then this meshless method came into picture by end of the century. By 2000, it was well established, starting with the SPH, smooth particle hydrodynamics was the first one, which was used in 1980s even. And then came to a variety of meshless methods, and then from there only the history of meshless methods starts. And here you see that this also last 3 decades, so much research has taken place in this area. So the meshless methods we can classify into based on formulation. You can see here strong form method, then weak form methods, and then hybrid methods. Different kinds of methods already developed. And then also how we are interpolation is done. You see that whenever we are throwing nodes, we are interpolating, and then between that how it is happening. And then so a variety of meshless methods, as I mentioned, has been already developed. And then with this, of course, not only meshless method, any simulation is concerned, we need to optimize. So you see that whenever we are trying to model an area in an aquifer system or even a river basins, we need to understand how much water is available, the quantity and quality. So there we need to say first go for simulation, and then we need to optimize where to put the wells at particular locations or how much water can be pumped. And for that we need optimization tools. So simulation optimization is the most powerful tools which we use in engineering. So that way here we try to connect this meshless method with various optimization tools, and then many problems have been solved, and large number of papers are published, and at least more than 10 PhDs also awarded in this area from my research group itself. So here simulation models, you see, we couple with the optimization tools, and then you see that generally you see that say for example whenever we are the optimization is concerned, we always want to minimize the costs and maximize the benefit. So that is the principle wherever we use for any kind of optimization. So that way, so here in modeling, there will be errors will be produced, and that error we are minimizing, or we're minimizing the concentration, or minimizing the cost involved. So like that, optimization tools can be used. And so here, this shows how we typical simulation optimization models works. So first we start with what kind of problem we are going to solve, and then you see that if you are going for meshless method, we can use particular meshless system, and then for the governing equations we'll be discretizing using a simulation models. And then once the simulation model is set up, so we'll be say connecting with an optimization tools as shown in this last point, identifying the best management method using optimization. And then we choose most optimal scenario. Say for example, for this campus, if you want to develop a water supply system, so how much water is required we can identify, and what is the potential available for the underground the groundwater system we can identify. And then we can say that okay, we are behind 3 or 4 or 5 wells in particular location, and then which location the most optimal way we can put it, and from that we go for the pumping. So we can put various scenarios and then identify. So that is the role of this simulation optimization model. So all the simulation optimization model for the groundwater, surface water, both the places we can use. And so variety of applications are there, like groundwater flow, so quantity identification, then reactive, multi-species reactive transport. So various simulation tools are there. And then simulation optimization is concerned, we can go for contaminant source identification, then recharge plants, contamination remediation plants we can have, then quantity and quality management. So variety of applications are there as far as simulation optimization models are concerned. So now, due to the limited time, I'll be going through the quickly how we do this kinds of modeling, especially using meshless method. Since we are talking about groundwater, so if you generally, so either you can go for 3-dimensional modeling or 2-dimensional modeling. So in 2-dimensional modeling, you can see that we can classify the aquifer system to confined aquifer or unconfined aquifer. So we are having say simulation equations, given equations like first equations so shows for unconfined aquifer system where head, so for any aquifer system for quantity assessments, so we need to identify what is the water level available at particular locations, and that will be by solving the equation number 1 and 2, wherever for confined, unconfined aquifer and unconfined aquifer, including pumping, recharge, and time and special variations we can capture. And these equations we will be solving for flow simulation. And then if we are having contaminant issue, so in 2 dimensions or 3 dimensions, we can solve it. And first, from the solution of the flow equations, we get the head variations. From the head variations, we go for the velocity calculations be done using Darcy's law, and that velocity component we will be putting for the contaminant transport equation as shown in the equation, the last equation, so which will be solving simultaneously. So that is so-called the simulation models. So here, as I mentioned, we are going for so we are discussing the finite difference, finite element, etc. Already well-established model, everybody knows it's. But here we are going for the meshless method. So meshless method, as I mentioned, instead of putting a grid or elements, we are only throwing nodes, and from the nodes we put we are connecting, we are discretizing these governing equations, and then we are trying to solve. So here, as I mentioned, variety of methods are available. One is the weak form and another one is strong form. So weak form is very similar to finite element methods, and earlier a strong form is very similar to finite difference method. So here both we can couple together also, and then we can have a meshless, I mean strong weak form, both are possible. So here what we do in very similar way, what we do in finite element, finite difference method, etc. So we discretize those governing equations which was earlier mentioned earlier for flow equation or transport equation, and those equations we can solve either using the strong form or weak form. So here finally we are discretizing the given equation to form an algebraic system, and there you can see so this way we can put it. So where we want to find a special variation of head so throughout the domain, so on the particular nodes as I mentioned, and then we can have the formulation. So all these formulations are so we can do it. So this will be the final formulation we are putting, and time is concerned, generally we will be using finite difference method only for the time, and from that we go for the flow, and from the flow calculations, so we get the head variation, and from the head variations we get the velocity variation, and using that velocity variation, that will be our input for the transport, contaminant transport simulation, and then we'll be solving the transport equation which I mentioned earlier. using this meshless method, either weak form or strong form. And then one is called RPCM. So the radial point collocation method, one is one of the most commonly used strong form of the meshless method, and other one is called meshless local petrogalerical method, which is the weak form. And both are shown here, and based upon that we go for the simulation. So here, as I mentioned, both methods now it is well established, and one is strong form has also its own advantage. So it is very easy to do, and there is no domain integration. But the weak form, we need to go for the domain integration. So both are also intercomparisons are possible. And here you see that we can club together the weak form and strong form together. So wherever actually weak form is due to the domain integration, we need to have the lot of computation time will be taken. So that is why we can also hybrid form is also possible, where we club with the weak form to the strong form. So that is wherever a divisional boundary condition is there, where the strong form is much more efficient, and wherever the flux boundary or Neumann boundary is there, so there the weak form is more efficient. So that is where both can be clubbed together, and it is called a meshless weak strong form methods, and that is the simulation model. So simulation models, we can go for strong form, weak form, and the hybrid meshless, the strong form and weak form. And optimization, as I mentioned, we can have a variety of optimization tools, starting from linear programming to all those things. But nowadays we go for the meta heuristics methods like particle sum optimization. Then there is differential evolution. So many methods are available. So here we use the simple particle sum optimization, where so we are having, say, we'll be using a set of sample, say based upon random number, we can have a particles identified, and these particles will be putting, so we need to calculate the position and velocity and its fitness. So the velocity update equation is given, and these are the standard formats nowadays used in many of the software also. So once so we start with the as a sample, I mean, using random numbers, we can get a number of particles, and based upon that, using those particles, we'll be calculating the velocities, and from there we can go for the simulation, the optimization tool called particle sum optimization. And as I was mentioning about meshless method, so here this shows how a localized meshless method will be working with a subdomain, how it will be connecting all the nodes, and then for a particular simulation, how we'll be doing. Okay, so now with respect to particle sum optimization, here you will see that, as I already mentioned, we are using the particle sum optimization, and the steps involved, we create the initial sum particles, and then initialization of the position and velocity of these particles will be done. And then we will be calculating the objective functions, so whether we want to minimize the cost or maximize the benefit. So based upon that, we can do the objective function will be calculated, and using that we'll be further going for the fitness calculation of the fitness. If the fitness is previous step was better, then the procedure can be terminated, otherwise it is continued, and then the steps are repeated until the stopping criteria is reached. So this is the way we develop the optimization tool. So these both the simulation and optimization, when we club together, we are having a very efficient model called simulation optimization model. So here I'll show some of the applications. So first one is a case study using a simulation optimization, how we use the meshless method for weak strong form method. So here, as I mentioned, this aquifer system, which is in Baroda, Vadodara region. So here, this aquifer, there is a river is on the left-hand side, there is a river, and then other side is it is a Mahi river one side, and other side there is a no-flow condition is there. So here you see that this aquifer system was simulated using this meshless method. So this is about, so here this aquifer system is around 150 square kilometer area has been modeled, and then there is the boundary conditions are shown, and then also the hydraulic conductivity is varying as shown here. And then aquifer details, as I mentioned, 5 zones are identified, and here so the number of pumping wells, 27 wells were there wherever the pumping takes place, and then there is a recharge of 1.2 million cubic meter per year takes place in this region. And here, so we simulated this model, so using almost, would say, 145 nodes. So that is the advantage of this particular method. So here you see that these no flow conditions and then flow conditions, so all those particular nodes are shown, how the gridding is, the nodes are distributed throughout the domain. And then so here the weak strong form method has been applied, and using this, so there is actually here we see that the middle there was a refinery was there, and that area was contaminated from the contamination taking place. As I mentioned, they were depositing their the leachate or the waste material there, and that has been say penetrating down to the aquifer system, and then aquifer got contaminated. And then this model was developed, and then we verified with available tools like finite difference method, finite tunnel method for the head variation, as well as the contaminant variation. We verified the model, and first for the flow and then transport. So here you see that the model was developed, and this shows the results, how the variations taking place. So here the flow variations, initially the first part is showing the head distribution after 7 years, how it is say varying with respect to various pumping and recharge using this meshless method we have already shown there. And then so here the purpose was how the meshless method can be efficiently done for such a large area, and in comparison with the finite difference method and finite tunnel method, this study was conducted, and then we have shown that it is can efficiently simulate the flow and transport phenomena in a large scale aquifer like that. And then second case study I would like to show is that, so as I mentioned, aquifer parameter estimation is one of the important problem in groundwater. So here a case study two where simulation optimization tools are used. So this is, we have done a study for a 4.5 square kilometer area in Surat, which is called this is a particular area, and this aquifer system. And here this was a 11 zone aquifer system which was already identified. So this data, whatever is available, so we used for, yeah, so he be used for the purpose of identifying the estimation of parameters. So this particular area. So here again, this shows we used around 1,000 sensor, which is much more intensive. The variation is there as far as hydraulic conductivity. So we used around 1,008 nodes in this particular aquifer system. And then here also the strong form method was used, and 150 strong form nodes and 158 weak form nodes were identified for this particular area. And then this shows with respect to flow simulation, how the head variation has taken place, and in comparison with the finite element model which we developed. And so the left-hand side figure shows the head simulation, say after say 7 years of simulation, how the head variation, and it was say verified with the finite element method. And then for parameter estimation, so as I mentioned, these are 12 more than 12 zones are there. So here so whatever the simulation model was developed for the aquifer parameter estimation. So there we connected with the meshless method, particle sum optimization, and here, so whatever the error coming with respect to, so initially we assumed the hydraulic conductivity at various locations, and then we simulated, and then using that we minimize with respect to the errors. So that was the way it was done. And so here this shows so here we used around 25 populations, and a number of iterations were 30. And here, so all the zones, so the actual transmissivity, and then this simulation optimization model, which was used in this case, you can see how accurately. So you can see that average error is less than say 5% error. Maximum is in one of the model 5%, and then all other models less than 5% error has been obtained by in this simulating in this the parameter as far as this case study is concerned. So here our aim was the application of simulation optimization model for the parameter estimation, how effectively we can use for this thing. So the last case study I would like to show is how we can use the simulation optimization model for optimal remediation of contaminant transports. So here an aquifer systems in Karnataka called Belgaum aquifer. So here this area is around 75 square kilometer area, and here also one industry was there as shown in this pond one number 1 and pond 2. So these were the industry where they put an alumina industry was there, and then they put the landfill there, and from there it was leaching down to the aquifer system, and there one river was passing on the bottom side called the Markandeya River. And then how this is flow and transport was simulated initially. So we studied the area, we collected all the aquifer properties, then the pumping, recharge, all those details were connected. And then source of contamination, as I mentioned, this is from this industry, and it was contaminating from 1970 onwards. And then so we need to first calculate the flow variation, then transport variation was captured. And so here again we use the meshless method. So here where we used around 1,585 nodes. So these red nodes indicate the strong form nodes, and then remaining the blue one indicate the strong form, and weak form indicate the red one, and both are connected together. And based upon that, so we use a time step for 25 days, and simulation was done for 30 years. So here this shows the flow variation, how the variation is taking place using the simulation models. And then so the contamination, as I mentioned here, the contamination was total dissolved solid, TDS. And here you see that we developed with respect to the meshless method, we developed the model, and then it was compared with the mod flow kind of models. And then we got a good match. And then we were putting, so with respect to various parameters, we use the sensitivity analysis, and then also finally a simulation model for flow and transport was established. And here, so our aim was, so here in this area, as you can see here, you see that most of the areas were contaminated, highly contaminated, around more than 1,800 ppm was the contamination, and we want to reduce so for to 750 milligram per liter, and we use the simulation optimization model based upon the meshless method and PSO. And here our remediation we put fixed for 4 years, and using so we use an objective function, minimize the with respect to pumping. So our pump and treat was put for the as far as a simulation optimization model. Objective was to pump the polluted water after stopping the contamination, and then treat the contaminated water outside the aquifer system. And then based upon that, various parameters were fixed, and then accordingly, so with respect to some constraints like concentration should be less than 750 ppm, and head should not fall below 750 meter from the sea level, and then recharge the pumping rate is between 0 to 1,000 meter cube per day. And so based upon that, we remediation time was fixed at 10 years, so to reduce below 750 ppm. And then this is the model which was finally the TDS we want to reduce below 750. So here we identified 8 pumping wells are considered for various locations for the remediation, and based upon that various parameters were fixed. And then so we are shown that the cost for this remediation will be around 1.67 crores rupees we need to spend to remediate this area using the simulation optimization model. So this shows the number of wells. So we need to put so 8 wells, and how much is to be pumped from various locations we identified as shown in this table. And then the remediation scheme was developed for this particular area. So finally, to conclude, so here you see that the high remediation costs are involved in these things. So simulation optimization models can be efficiently used for groundwater remediation. So groundwater, as I mentioned, it is a say one of the most important source where we get fresh water. Almost 99% of the available fresh water is from groundwater, and we use the much water for various drinking as well as irrigation and all the uses. And so sustainable management, we need to study the area using simulation, and then optimization tools are required. So here what I've shown is that the latest development in this area, so how we can have the modern techniques like measures method for simulation, and then simulation optimization tools for say the quantity assessment, quality assessments, and then also the parameter estimation, and then also remediation, how we can develop very efficient models using the meshless based simulation models, and then optimization models using PSO. So here you see that these kinds of hybrid techniques, so very effectively we can utilize, and then based upon that we have developed a number of tools. And now so the next future scope in this area include like we can connect with the artificial intelligence and machine learning tools with respect to these kinds of simulation optimization tools, and then we can further assess say for a particular area how the variation taking place, and then say the we can so these kinds of, so with the changing water resource scenario, like due to the climate change or the high contamination problems, so we need to have very sophisticated tools, like then simulation optimization is one of the most important tools which we can use, and there we can connect with various techniques like artificial intelligence, AI, ML tools also we can connect together, and then we can have efficiently assess how the variation is taking place, how the developments can take place as far as this area is concerned. So with this, due to the, as already organizers told, it is due to lack of time, I am stopping here. So thank you very much for the invitation here. So if you have got any questions, quick questions, I'll be happy to answer, since one more keynote is awaited. So if you have got any quick questions, I'll be very happy to answer. Thank you very much. Any quick questions? No. Yeah, please. Yeah. Yeah, yeah. 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 So only say, as I mentioned, the groundwater is one of the most important source of water. So in India, since India is the country which takes maximum groundwater as far as a resource is concerned. So here, so what is now happening in Punjab, Haryana, or many areas, as I already mentioned in my earlier slides, I show how the variation is taking place. So many areas are stressed. So here we need to say for indicated, say model, not modeling, but indicated use of surface water and groundwater, and then also go for the indicated water source planning. So where we need to go for maximum, say like now today, Professor Tengaraj was telling in the morning that now we cannot construct big dams since everywhere a lot of opposition is there, environmentalists are opposing. So wherever local scale, how we can deal with the available water with respect to available, say rainfall available, say recharge available surface water and groundwater, how we can utilize local scale planning is much more important than say for the entire country we cannot say, for the even entire state we cannot say. So like say water conservation measures like rainwater harvesting or recharge measures, or so wherever locally available. So that is where the most important aspects we need to put, like Gandhi was telling Gram Swaraj. So wherever the in a village or in an area, how we can effectively utilize available water in its own way and its own way, how we can conserve. So that is the best way of planning. So not like if you construct a big dam and like say earlier there was interlinking or river plants were there, but it is though in a large scale we can only certain location it is possible, but in a huge scale if you implement there will be another lot of environmental issues, lot of environmental problems, or even now climate change. Wherever we are getting normal rainfall, that is less rainfall and the reverse trend is taking place. So that way we cannot look into for a large scale, but we need locally available water, how we can conserve, how we can recharge, how we can use more efficiently, more effectively. So that is where we should plan, since otherwise it is a very difficult way we can go. But of course, like now, earlier we were suffering from availability of data, but now with the modern tools like remote sensing, with satellite data, all those things are available. So we can have a local scale, and that is where all these institutions have to come their own way, their own areas or their own states. If they work and come up with various plans, so that is the best way to sort out all these issues. So of course, whatever we talked is the high level modeling, all those things. So that may not be so essential in many areas, but practically how we can solve. So that is where the issues to be dealt with. Yeah. Yeah. So other professor is waiting. Okay.
Yeah, because of time limit, we are just winding up this up. Sir will be available here. You can ask him the questions whenever you be free. Okay.
So thank you so much, sir, for the valuable and engaging presentation. Now, I request Professor M.K. Chowdhury, sir, to kindly present the token of appreciation memento to Professor T.I. Eldo.
Sir, please come to the stage, sir. Sorry, you left.
So now let me move to our next inaugural keynote. Up next, we have another distinguished keynote speaker, Professor Carlo Gulattieri, a leading voice in European environmental hydraulics and computational fluid mechanics at the University of Napoli. He has devoted his entire academic career to Napoli, earning his BSc in hydraulic engineering, MSc and PhD in environmental engineering, and now serving as associate professor in the civil construction and environmental engineering department. He has authored one or two peer-reviewed papers, including 25 journal articles and 53 conference papers, as well as textbooks on hydraulics and environmental hydraulics. Since 2006, he has served on the editorial boards of prestigious journals and earned the Outstanding Reviewer Award in 2012. His comprehensive scholarship, editorial leadership, and global engagement illustrate the best of European engineering in the tackling today's urgent water challenges. So now I would like to I would like you all to join me in warmly welcoming Professor Carlo Gulattieri to deliver his keynote address. He will be joining us online.
So I'll just cancel this and we'll rejoin this for start. Will you join?
I request the participants to wait little. He's joining online. Okay. Since we are already running late of 1 hour, so
Entering. Okay, thank you. Thank you. Good afternoon.
Yeah, good afternoon, sir. You're audible, sir. You can share the screen.
Yes.
Give one more, sir. Just camera. You can turn on the
Can
camera.
you see my?
Hello, sir. Yeah. Hi, sir. It's Dr. Akash. Yeah, your screen is visible, sir, but you can share the PPT.
Hello?
Your screen is visible, but you can share the presentation. Just yeah, is your presentation visible? Yes.
Okay.
Yeah. It's
So I can start
yes, yes. You can give the full screen.
the full screen.
Yeah. Yeah. Give the presentation. Slideshow. You can start the slideshow. It's down just near that minus plus sign is there. Zoom in, zoom out. Just near to that. That right side down corner. That zoom in, zoom out is there, sir. Just near to that.
Mm,
Yeah.
I can see that.
Yeah. If you click on that, it will be full screen. Or you can give from the presentation drop down menus there, the top.
It's okay.
Nothing has changed now. Is it changed your side?
Yes.
No, no, no. From no. Sir, yeah, sir. You can share once again. Share your screen once again, and you can do the normal way.
Okay. Okay. Okay.
Okay, sir. You can start this way only. If the presentation is not coming, okay, you can just continue this way itself. Yeah.
It's okay. You can see the screen. You can see my screen.
Yeah, you can start, sir. It's visible.
Okay.
Yeah.
Okay. Okay. So good afternoon, everybody. So the title of my presentation is about river conferences, current issues, and field methodologies. So first, I would like to uh, acknowledge the contribution of many colleagues because my research on river conference was done in the last decade, was carried out with many colleagues from different countries, from Brazil, from the United States, from Chile, from China. So I would like to thank them for working with me on that. And this is the outline of my presentation. We need first to understand what are river confluences, which are the main drivers controlling the hydrodynamics and morphodynamics and ecology at confluences. next we will see the instrumentation that we are basically using in the field studies. We will see next how the data collected in the field are analyzed. Next, I will show you some result about field study or river conference, different scales. Some of those are the studies in which I working, and finally some conclusions. So let's see first what are river conferences. They are nodes in fluvial networks. They are characterized by a very complex hydrodynamics and morphodynamics, and they have even important ecological function. We call the conference hydrodynamic zone the area around the conference in which hydrodynamics and morphodynamics are affected by the conference. We know that four are the main, we have basically four main drivers of hydrodynamics and morphodynamics at conferences. They are the geometry of the conference, the junction angle, and more generally the conference platform. And second, the momentum flux ratio between the two tributaries merging as the conference. Sometimes we consider even the discharge ratio as well as the velocity ratio as two factors important. And third driver is the degree of concordance of the weather of two rivers in terms of conference. Finally, we see that difference in water density can play a role in dynamics and morphodynamic conference. This what is a not simultaneous conference. So, and this is one of the largest conferences in the world, the conference between the Negro River and the Solimões River, the Black River, the White Solimões River in Brazil. We are in the Amazon River basin. And this is the largest conference, the conference between the Madeira River and the Amazon River, still in the Amazon basin. Other examples of conferences in Europe and again in South Africa, the conference. You can see in this case we have a difference in the concentration of the sediment in the distributors. No, it's working. It's working again. It's working again. Okay. Yes, I lost the connection with you. Okay. Yeah, it's okay. Yes, because this slide is showing the typical hydrodynamics and morphodynamics characteristics in the conference hydrodynamic zone. We can see that first we have on the right left corner on the top we have the stagnation zone. Next, the tributary needs to enter the confluence, so it needs to adjust the trajectory to enter the confluence, so you have a flow deflection zone. And that downstream, we have even a flow separation zone, just this is a blue one. And on the right side, we have the maximum velocity because, of course, the cross section is narrowing, so we have a maximum velocity region. And at the downstream, the flow is recovering gradually, moving in the post-confluence channel. In terms of morphodynamics, we see that the blue area means area in which we have a deposition of suspended sediment, while the orange area is an area in which we have erosion. Another important issue could be if the tributary has or not a temporary or permanent floodplain. We have some example of confluence in which we have a tributary with floodplain. This is a case of the confluence between the Yangtze River and the Poyang Lake in China. Again, the confluence between the Yangtze River and the Dongting Lake, and even in South America, the confluence between the Negro River and the Branco River. Another important factor that we should consider is any difference in density of the water between the two tributaries, because density difference can affect significantly flow structure at the confluence. We have at the end a lateral stratification at the junction, and as we have even, of course, a horizontal shear layer, so we have basically both velocity and density gradients in the horizontal direction. And at the end, this effect can result in a mixing interface, which is not vertical, but is inclined. And we will see how this can affect very significantly the flow patterns at the confluence. This is a case, for example, of the confluence between the Negro River and the Solimões River, the confluence we have seen before, as well even that on between the Yangtze River and the Poyang Lake. So there are many cases in which we have density difference between the two, the water of two tributaries, because they are belonging to different river basin. So the waters have different characteristics in terms of suspended sediment, in terms of temperature, in terms of conductivity, and this leads to a difference in density of the water. On the left, we can see how we have the mixing in the confluence between the Negro and the Solimões rivers. We can see how there is a density current of water from the Solimões side moving at the bed into the Negro side. The same situation we have even on the right figure, in which we have the confluence between the Poyang Lake and the Yangtze River in China. We have in some conditions, some flow condition, the Yangtze River water are denser than the water of the Poyang Lake, while in other flow condition we have the opposite effect. So it means that the Poyang Lake water is denser than the Yangtze River water. So let's move to the instrumentation that we are using in the field. The first basic, very basic instrumentation that we are applying is the acoustic Doppler current profile, which is a standard method to measure velocity and discharge in a large river. We can even estimate after calibration the suspended sediment concentration. So basically, the instrumentation is moving from one side to the other side of the river to get those data. And we can use even the DCP even in using a fixed vessel. So we can use locate the instrumentation in one place of the river to get velocity measurement, velocity data in that place. But generally speaking, the moving vessel approach is much more applied to get, because we can get the velocity distribution in the cross section of the river as well as the discharge in the river. There are two examples of results from the Amazon River. We can see the distribution of the velocity cross section, the cross-sectional distribution of the velocity in two different flow conditions. On the top, we have basically low flow condition. On the bottom, we have high flow condition, because we are in July. Basically, in the Amazon River, the low flow condition as in October, November, while the high flow condition are in July. So there is large difference in terms of discharge. Again, we can see this is a distribution of the DCP backscatter, the average backscatter, that we can apply to derive the distribution of suspended sediment. This is a cross section just downstream of an island, a big island inside the Amazon River. Again, this is a distribution, the cross-sectional distribution of the average backscatter for the same flow condition, the same location. Manakapuru is a station in the Amazon River. About river morphodynamics, we can use different instrumentation. We can use multi-beam or single-beam echo sounder. So we have two types of echo sounder. We can do bed sampling, of course, and we can apply remote sensing methods, because we can use download it and even analyze the picture from many satellites. For example, we can derive the particle size distribution. We have data at the Orinoco River. On the right, we can see, please. No, and the line 21. Yeah. Okay, and we can see how we have on the right is an image taken by Google Earth of this is again the conference between the Negro River and the Solimos River in the Amazon River basin. For example, the analysis of Landsat images was applied to identify any morphological change in the planform of the confluence between the Meta River and the Orinoco River. We are in South America. The Orinoco is the third largest river in the world in terms of discharge, and we can see how from 1973 to 2014, how the junction angle of the confluence, as well as the location of the confluence, was migrated at some instance. This is the picture on the left is showing the characteristic of the bed morphology. We are again by a multi-beam system. We are again in the Amazon River. We are in the station of Jatuarana, which is about 50 kilometers downstream of the confluence between Negro River and the Amazon River. We can see how this data can be applied to identify the characteristic of the bed form that we have on the bed of the channel. This is another example of morphodynamic studies. We are again in the Orinoco, the city of Ciudad Bolivar. We are studying about basically we are studying the change in the aerodynamics and the morphodynamics around an island in the Orinoco River. Using a single beam system and a DCP, we can identify the change in the elevation in the river. So even we can estimate the volume of erosion and deposition of sediment around the island. About water chemistry or water quality, we can make, of course, water sampling. We can apply a multiparametric profiling to get vertical profile of many water quality parameters. On the left, we see the conductivity. This is a cross section in the Amazon River. We can see how the conductivity is changing over the depth in 3 different vertical position in the cross section of the river. On the right, we can see the distribution of suspended sediment in the same river. So let's see how we can analyze our data. The data collected basically with a DCP can be applied to derive many parameters of the river. Hydraulic geometry parameters such as cross-sectional area, channel width, wetted perimeters, hydraulics, radio, aspect ratio, the depth. We can get a lot of information about the geometry of the section, as well about the velocity, cross-sectional velocity, median, depth, average velocity, flow direction, even through the Reynolds number. So we can get many information about the basic characteristic of the river in that section. In addition, we can calculate Coriolis coefficient, Bussinet's coefficient. We are using those coefficients in hydraulic modeling, so it is very important to derive those parameters. We can even estimate any friction coefficient, Manning and Chassis coefficient. We can get these parameters that are applied in hydraulic modeling. On the right, we can see the picture is showing the longitudinal distribution of Bussinet's coefficient in the Orinoco River. We can see some pattern related to the change in the width of the channel. Even there is an island. So these affect the distribution of the velocity and even of the Bussinet's coefficient. We can even derive the, please. Okay, so let's see. We can get very rapidly. We can get even the shear velocity. We can identify the Rouse number for sediment, so we can identify the mode of sediment transport. We can get the distribution of suspended sediment. There is a more advanced post-processing tools. Is a velocity mapping toolbox that can be applied to map. For example, this is a map of the depth average velocity in the Orinoco River, secondary flow. And let's move to some results. We have defined 3 types of conference: small scale, medium scale, and large scale, depending on the channel aspect ratio. And this is a very small conference in the US. It was very largely studied in the 19, even about 20 years ago. And I would like to show you the result in the larger conference, in a larger conference that between the Negro River and the Solimois River. We can see the map is showing the distribution of the transect that were collected during that study. So we got many information about the geometry characteristic, main flow properties, water chemistry characteristic of those rivers. And this is again on the left, on the right. This is a map of the depth average velocity at the confluence, so we can see how the 2 rivers are interacting and merging together. The transfer of momentum from the Solimois River and to the Negro River. This is a map of the depth average velocity in which we can identify the basic zones of the confluence hydrodynamic zone. So this stagnation zone, separation zone, maximum velocity zone, etc. This is the cross-sectional distribution of the velocity and the backscatter, so we can see the secondary flow. This is the location. This picture is showing the location of the mixing interface at the bed as a free surface. So we can study how the two rivers are mixing together. We can compare different flow conditions. We can see how the mixing is progressing, moving to downstream in the post-confluence channel. And the main result was that we found a gravity current from Solimas to Negro, which is affecting mixing. But we can study even ecology or river conferences. This is a study we did in the Amazon, in which we compare the distribution of fish larvae and with a metric M2, which is basically representing the velocity gradient. So the bioenergetic, the effort done by fish to move from one point to another point, in which we have a velocity gradient. So basically, this metric can be applied to identify aquatic species abundance and richness. So at the end, my conclusion that the conference are not in fluid networks, which are characterized by a very complex change in hydrodynamics and morphodynamics. They have even important ecological function. The drivers of the structure of the flow at the confluence are the geometry of the confluence, the momentum flux ratio, the degree of concordance of the channel beds, and even in many cases, even difference water density. The knowledge about hydrodynamics and morphodynamics of confluence increased significantly during the last years, even for the growing application of modern field investigation technologies and advanced post-processing and analysis methods. Finally, even we have seen very shortly, in short, that even remotely centered image-based techniques can be applied to identify confluence platform temporal evolution, suspended sediment dynamics, as well as the flow structure at the free surface. Let's go. If you have if you have some questions, I'm available. Maybe we have a few minutes for some questions. Yes, yes. I think that we are. If you have some questions, yes, yes. I think it's time for any questions. If there is any question.
So thank you, sir, for the valuable section. Actually, he was originally scheduled to join us in person for this AWaRe, but due to some unavoidable circumstances, yes, sir.
Please.
Sir, we are concluding the session, sir. So we are giving thanks and all.
Okay, you are welcome. Bye bye. Bye bye.
Yeah, thank you for joining, sir.
Bye bye.
Okay, with this, we conclude our inaugural keynote. Thank you all for being with us for this section. Thank you.
Yeah, all of requested to go for the lunch. It's been arranged in the faculty guest house. Okay. Bus is there, right? Yeah, bus is available. So after the lunch, the session will be continuing in the civil auditorium.